When we have a time series of data with no particular pattern, then we can't use the method of moving averages. An alternative method is called exponential smoothing, and it works as follows. We basically, for each forecast, we take the previous forecast and then we compensate by seeing what actually happened that previous time, and we make a correction. Let's see how it works here. The first piece of data is 13, so our best guess for the next prediction is the same as we had before, so 13. The forecast for the next time will equal the previous one plus a correction term, and that correction term is proportional to the error. We guessed 13, the actual value was 9. So we need to add on something proportional to that difference. And we'll see how we choose the proportionality term. Let's try 0.3 to start with. So we want 0.3 times how wrong we were, A3 minus what we actually got. And that gives us 11.8. Then we just do exactly the same by clicking and dragging all the way down. All the time we're adjusting for how wrong our forecast is compared with what we actually got. So we're sort of tracking the data, and of course what we're really interested in is the next one, because that will be our forecast for the next time. Let's see how this looks on a graph if we compare these two sets of data, the actual and the forecast. So I'll highlight the two sets, go to Insert, go to Line Graph, and there we see what's happening. We've got the very jagged set of data going nowhere in particular, and what we see here is that the forecast data is following it, doesn't start till time 2, and it tends to iron out the extremities. It doesn't go as high and it doesn't go as low, so it's slightly smoothed out what's really happening. Let's now see the effect of changing that constant. 0.3 means that actually we don't take a lot of notice of the error. We just rely on the previous forecast, which in itself relied on the one before that. So you get quite a slow variation. This line is not changing very fast. It's not being influenced too much by what's actually happening with the real data. Now suppose instead of 0.3 we had, say, 0.8, a number nearer 1. I'll put that in, and then to load that everywhere else I have to click and drag it down the whole way. And now I get this data. What we can see now is that the forecast is very much echoing, following the original data. It's almost exactly going in parallel, but just one step behind. What's happening now is that when we add on the correction, we're adding on almost the whole of that correction, so what we get each time is very close to the previous actual results. That's why the graphs are, as I say, effectively tracking each other. So it depends what you think is most important. If the most recent data is important, you need a high value of your constant near 1. If you think that the latest data is not very reliable, and that really we just want to go on what happened over the past several time periods, then we'll have a low value for this constant. So this is exponential smoothing.